When I first looked at it, I felt nothing. No awe, no curiosity, no sense of danger. Just a dark smudge in the sky. A place astronomers once dismissed as empty space. But that emptiness was a lie, because behind that, darkness behind layers of dust, thick enough to erase stars from existence, something was hiding. Something so large that once we finally saw it, it forced us to admit a terrifying truth. The Milky Way was never fully mapped, and its largest star was hiding in plain sight. I remember the first time I saw the image, not a photograph you'd hang on a wall, not a glowing nebula or a spiral galaxy bursting with color, just a grainy infrared map of the Milky Way's inner regions patched with reds, blacks, and faint glows that looked like noise more than structure at first glance. Nothing about it felt important, but the longer I stared, the more unsettling it became. Because this wasn't empty space, this was blocked space, a region where visible light simply died. For decades, astronomers pointed their telescopes here and saw almost nothing. No bright stars, no shining clusters, just darkness where something should have been. And in astronomy, darkness doesn't mean absence. It means obstruction, interstellar dust. The same dust that forms planets, stars, and life also acts like a cosmic blindfold. It absorbs visible light, scatters it, and turns entire regions of the galaxy into voids. 2 optical telescopes, these areas look dead, uninteresting, easy to ignore. And so, for most of the 20th century, this part of the Milky Way was ignored. I imagine astronomers flipping past it, page after page, survey after survey. Nothing to see here, move on. But the galaxy doesn't care what we think is interesting. It hides its biggest secrets behind inconvenience. I didn't understand that at first, neither did they. Because if you had asked anyone back then where the largest star in the Milky Way was hiding, no one would have pointed here. Not behind this wall of dust. Not in this supposedly unremarkable region of the Scutum constellation. And yet, this is exactly where the trail begins. A trail that leads to a star so large that our sun becomes a rounding error. The illusion of emptiness. To understand how this happened, I had to rethink how I imagine space. We like to picture the galaxy as open and transparent stars, shining clearly against a black background. But that's a lie, created by visible light. The Milky Way isn't clean, it's cluttered, choked with gas and dust. And nowhere is that more true than in its inner spiral arms. Here, dust lanes cut across star fields like scars. They swallow light completely. A star can be blazing with unimaginable energy and still appear faint or invisible. Enough dust sits between it and us. This region looked empty because our eyes were blind to it. Infrared light, however, tells a different story. Infrared doesn't care as much about dust. Its longer wavelengths slip through where visible light gets trapped. And when astronomers finally began mapping the Milky Way in infrared, the illusion shattered. Suddenly, the darkness lit up, not with 1 or 2 stars, but with dozens of giants. Red supergiants, massive, bloated stars at the end of their lives, rare, short-lived, and terrifyingly unstable. Finding 1 red supergiant is unusual. Finding 2 is exciting. Finding over 20 in one place, that shouldn't happen. And yet, here they were, hidden behind the dust, waiting the first unease. I dug deeper into this region's history. A strange feeling crept in. This wasn't a discovery story filled with dramatic moments or sudden realizations. No one gasped at a telescope and shouted, "There it is." Instead, it unfolded quietly, too quietly, the kind of quiet that makes you uneasy after the fact. Because when something this large goes unnoticed for decades, it raises an uncomfortable question. What else are we missing? The cluster would later be called Stephenson 2, named after astronomer Charles Bruce Stephenson, whose work focused on something most people never think about: catalogs, lists, coordinates, the unglamorous foundation of astronomy. He wasn't hunting monsters, he was organizing stars, and unknowingly, he was drawing the first rough map to the largest star ever confirmed in our galaxy. But at the time, Stephenson 2218 was just another entry. A dot, a strange one, yes, bright, red, oddly luminous through dust, but not yet terrifying, not yet impossible. A star that didn't fit. What unsettles me most is how normal this all seemed at first. No alarms, no headlines, just data that didn't quite behave. Infrared brightness that was too strong, a color that was too red, a luminosity that didn't shrink even after accounting for dust, the kind of anomaly that whispers instead of screams. And whispers are easier to ignore. But science doesn't forget anomalies. It stacks them. And as I followed the trail backward from modern measurements to early infrared surveys, realized something chilling. This star had been telling us what it was all along. We just weren't ready to listen. So if the largest star in the Milky Way could hide behind dust, dismissed as emptiness, for decades, what happens when we finally look deeper and realize this was never the only giant hiding in the dark? Nothing about it felt heroic. No countdowns, no flashing screens, no moment where the universe seemed to pause. Just lists, rows of numbers, coordinates, brightness values, written in ink that no one expected to change history. And yet, this is where the journey truly began, because the largest star in the Milky Way was not discovered by someone looking for it. It was discovered by someone organizing what everyone else overlooked. And that should make you uncomfortable. The quiet work no one watches. When I imagine great discoveries in astronomy, I picture telescopes aimed at the sky, scientists staring at screens, gasping when something impossible appears. That's the story we like to tell. But Stephenson 218 did not emerge from drama. It emerged from paperwork. In the late 20th century, astronomy was undergoing a quiet transformation. Digital imaging was still crude by modern standards. Infrared detectors existed, but they were expensive, limited, and difficult to use. Most large surveys still favored visible light because it was familiar, reliable, and well understood. And visible light had already made its judgment. This region of the Milky Way was boring to dusty, too obscured, too empty to bother with, which is why very few astronomers focused on it. Charles Bruce Stephenson was one of them. He wasn't chasing cosmic wonders. He wasn't hunting black holes or supernova. His work was slow, methodical, and deeply unglamorous. He built catalogs to most people. A catalog sounds like a book of answers to astronomers. It's a book of questions waiting to be asked. Stephenson's catalogs were lists of stars that stood out, stars that were unusually red, unusually bright in infrared, or strangely positioned in crowded regions of the galaxy. These weren't conclusions. They were flags, markers that said, something is here, but nothing more. Why red supergiants matter? Stephenson focused on a specific type of star, red supergiants. And this is where the unease begins. Red supergiants are massive stars in the final stages of their lives. They are not stable. They are not quiet. They are swollen, bloated, and losing material into space at astonishing rates. They burn fast, they die young, and they are rare. The galaxy should not have many of them visible at once, which is why cataloging them matters. If you find too many red supergiants in one region, something is wrong, or something extraordinary happened there. Massive stars form together, evolve together, and die together. So, a cluster full of red supergiants means the past was violent. A burst of star formation, huge amounts of mass, stars born already doomed. Stephenson wasn't searching for the largest star ever discovered. He was searching for patterns, and patterns are dangerous things. The cluster that shouldn't exist. Stephenson compiled his lists. Something strange emerged. Groups, clusters. Not just one red supergiant here and there, but many, concentrated in the same regions of the sky. That alone was unsettling. Red supergiants aren't supposed to clump together in large numbers. Their lives are short. Their timing must align perfectly. Finding more than a handful together is rare. But here, behind the dust, in a region thought to be empty, Stephenson's data hinted at something far larger. A cluster, not visible in optical light, not obvious in early surveys, but undeniable once infrared data was considered. This cluster would eventually be named Stephenson 2. At the time, it was just another entry. Coordinates, magnitudes, a note in the margin, but something about it didn't sit right. The problem with dust is the villain of this story. Interstellar. Dust doesn't just block light, it lies. It makes stars appear dimmer than they are, redder than they are, smaller than they are. If you don't correct for dust properly, you misunderstand everything. And in the 1990s, dust correction was crude. Astronomers knew dust existed, but its behavior varied wildly from region to region. The Milky Way's inner spiral arms were especially chaotic, thick clouds, overlapping structures, unpredictable extinction. Stephenson knew this, which is why he leaned into infrared. Infrared doesn't remove dust entirely, but it reduces its power. It gives you a hint of what's really there, and what infrared revealed in this region was disturbing. Stars that were bright, even through dust, stars that shouldn't look that luminous unless something extreme was happening. Among them was one entry that refused to behave, a star that later became known as Stephenson 2-18. At first, it didn't scream largest star ever. It whispered outlier. An outlier in the data. Find this part unsettling, because it shows how discovery often begins, not with certainty, but with discomfort. Stephenson 2-18 didn't break rules outright. It bent them. Its infrared brightness was unusually strong. Its color was extremely red. Its luminosity estimates were high even when dust was accounted for. Conservatively, but not high enough to cause alarm. Just high enough to cause hesitation. And hesitation is where discoveries stall, because when data doesn't fit, you have two choices: investigate it, or assume it's wrong. Most anomalies die quietly that way, but this one didn't. Every time astronomers adjusted the dust correction, the star remained too bright. Every time distance estimates shifted slightly, the numbers stayed uncomfortable. It refused to shrink into normalcy. The map without the monster. Here's what haunts me most about this phase of this story. Stephenson mapped the region. He identified the cluster. He cataloged the stars. And yet, no one realized what they had found, because discovery isn't just about data, it's about context. At the time, astronomers didn't fully understand the upper limits of red supergiant size. Hypergiants were poorly defined. Distance measurements were uncertain. Infrared resolution was limited. The tools weren't ready. So the monster stayed hidden, not because it was invisible, but because it didn't yet have a name. Stephenson 2218 was just another dot. A strange ... but still a dot. The danger of incomplete maps. As I followed the timeline forward, I realized something deeply unsettling. This wasn't an isolated failure. It was systemic. Astronomy depends on maps. Maps depend on light. And light lies when dust gets involved, which means entire regions of our galaxy were mischaracterized for decades. Not unknown, misunderstood. We didn't know what we were missing because our maps told us nothing was there. And Stephenson 2 was the first crack in that illusion. The cluster reveals itself as infrared surveys improved. Stephenson 2 transformed from a curiosity into a shock. Dozens of red supergiants, not scattered, grouped, packed into a region that should have been quiet. This wasn't just a cluster. It was one of the most massive known open clusters in the Milky Way. A place where huge stars formed together, lived fast, and were now dying together. And somewhere inside it, something was brighter, larger, wrong. But no one could yet say how wrong. Why no? One panicked. This is where I expected panic. Headlines. Excitement. Instead, there was caution, because claiming the largest star ever discovered is dangerous. Extraordinary claims demand extraordinary certainty, and certainty was still missing. Distances were fuzzy. Dust corrections were evolving. Spectral classifications were improving but incomplete. Astronomers knew something strange was here. They just didn't know how far it went. And that uncertainty kept the terror contained. For now, the map was finished, but the story was not. Stephenson's work ended quietly. He built the map. Others would follow it. And that's the most unsettling realization of all. The largest star in the Milky Way wasn't discovered by someone looking for greatness. It was discovered because someone refused to ignore the invisible, which means the galaxy didn't reveal its secret willingly. It was cornered, and it still hadn't shown its full size. If a simple cataloged just lists and coordinates was enough to uncover a cluster of dying giants, what happens when we finally focus on the one star in that cluster that refuses to obey the rules? There are places in the universe where stars are born, and there are places where stars go to die. What unsettled me was realizing that Stephenson 2 was not simply a cluster of stars. It was a graveyard in progress. Because when stars this massive begin dying together, it means something catastrophic happened in the past and something inevitable is coming next. The first time the numbers felt wrong, I didn't understand the danger at first. I was still thinking in terms of individual stars, isolated objects burning quietly in the dark. That's how we're taught to imagine stellar death. One star collapses. One star explodes. One story at a time. Stephenson, too, shattered that illusion. This was not a lone giant nearing the end of its life. This was a crowd of giants, all swollen, unstable, and ticking toward collapse at nearly the same cosmic moment. And that changes everything. When astronomers finally resolved the cluster clearly in infrared, the picture became impossible to ignore. Not one, not five, but dozens of red supergiants, all packed into a region that by the rules of stellar evolution should never host that many at once. Red supergiants are rare because they don't last long. Their lifetimes are measured in hundreds of thousands of years, sometimes less. On cosmic timescales, that's nothing. So to find so many together means they were born together, which means something enormous happened here, reconstructing a violent past. I tried to imagine what this region looked like millions of years ago, before the dust settled, before the giants swelled, before the quiet began. Stephenson, too, was once a storm. A massive cloud of gas collapsed under its own gravity, fragmenting into countless dense knots. Each knot became a star, but not ordinary stars. These were monsters from birth, stars with 10, 20, even 40 times the mass of the sun, stars that burned violently from the moment they ignited. The cluster must have formed in a burst, a rapid, intense episode of star formation that poured enormous mass into a confined region of space. This kind of event doesn't happen gently. It requires shock waves, compression, and overwhelming gravitational collapse. Something triggered it. Perhaps a nearby supernova. Perhaps a spiral arm density wave. Perhaps the collision of gas clouds. Whatever it was, it created a cluster destined to burn bright and die fast. And now, millions of years later, we were seeing the aftermath. Why red supergiants are a warning sign. Red supergiants are not calm stars. They are stars that have lost control. Once a massive star exhausts hydrogen in its core, it begins burning heavier elements. The balance between gravity and radiation pressure shifts. The core contracts. The outer layers inflate. The star swells, sometimes to hundreds of times the sun's radius, sometimes more. This expansion cools the surface, giving the star its deep red color, but that color is deceptive. Beneath it, the star is burning fuel faster than ever. Red supergiants leak matter into space constantly. Their gravity at the surface is weak. Their outer layers drift away in massive stellar winds. They are unstable by definition, and Stephenson, too, had over 25 of them. That alone made it one of the most extreme clusters known in the Milky Way. But it wasn't just the number that bothered me. It was the consistency. A synchronized ending. Clusters age together. Stars in a cluster form at roughly the same time from the same material. Their mass determines how quickly they evolve. The most massive stars die first. Less massive ones follow. Stephenson, too, was at a very specific age, between 14 and 20 million years old. That age range is critical. It's old enough that the most massive stars have already exploded as supernova, but young enough that many slightly less massive stars have just entered the red supergiant phase. That means we were catching the cluster at a rare transitional moment, a moment where dozens of giants were nearing the end together, a moment that does not last long. This made Stephenson to more than a curiosity. It made it a countdown. The unease of proximity, another detail, kept nagging at me. The red supergiants weren't spread out, they were crowded, packed into a region only a few light years across. That closeness matters. When massive stars evolve and die near each other, they don't do so in isolation. Their winds interact. Their radiation shapes the environment. Their eventual supernova can trigger or suppress future star formation. Stephenson, too, was not a quiet place. It was an environment shaped by violence past, present, and future. And somewhere in the middle of that chaos, one star was brighter, the one that refused to blend in at first. Stephenson 2218 didn't look terrifying. It looked slightly wrong. Among giants, it was more luminous. Among red stars, it was redder. Among infrared sources, it burned too strongly. If you weren't paying attention, you could dismiss it. Crowded fields are messy. Measurements overlap. Dust complicates everything. But as astronomers refined the cluster's properties, this star kept refusing to settle into place. When plotted on luminosity temperature diagrams, it sat above the others. When compared against stellar evolution models, it strained the limits. When corrected for dust, it grew larger instead of shrinking. It was not just the biggest in the cluster, it was out of scale with the cluster itself. And that is when the fear started to creep in. Breaking the statistical comfort zone. Astronomy relies heavily on statistics. If one object behaves strangely, you question the data. If many behave the same way, you revise the theory. Stephenson 2218 was dangerous because it was singular. There was no average to hide behind, no curve to smooth it out. It stood alone at the edge of every graph, too luminous for its temperature, too cool for its brightness, too large for comfort. At this stage, astronomers still hesitated. The cluster was extreme. Perhaps the star was just an extreme member of an extreme Scrage population. But that explanation grew thinner with every observation. The role of infrared truth. The more I studied this, the more I realized how much infrared astronomy had changed the story. Invisible light. Stephenson 2 barely exists. In infrared, it dominates. Infrared allowed astronomers to see through the dust and compare stars fairly. It reduced the lies dust tells. It didn't eliminate uncertainty, and that uncertainty worked in the star's favor. Every conservative assumption still produced an enormous star. Every cautious correction still placed it at the top. The star refused to shrink into safety. The psychological shift. This is where the tone changed. Not dramatically, quietly. Papers began using words like anomalous, extreme, unusual. These are careful words. Scientists don't write terrifying, but I could feel it between the lines. Stephenson 218 was becoming a problem. Cluster that amplified the threat. What made this worse was its environment. If Stephenson 2218 had been alone, it might have been dismissed longer. But inside Stephenson 2, surrounded by other red supergiants, it had no excuse to stand out. It was brighter than giants, already considered enormous, cooler than stars, already near the limit. It didn't just exceed expectations, it exceeded exceeding expectations. That's when the scale started to crack. Standing at the edge without realizing it. Looking back, what unsettles me most is how close astronomers were to the truth without seeing it fully. They had the cluster, they had the star, they had the data. What they lacked was the final alignment of understanding distance. Dust correction, spectroscopy, precise enough to lock the temperature. Those pieces were coming, slowly, relentlessly, and when they arrived, the story would change from strange to absurd. But not yet. For now, Stephenson 2 remained a cluster of dying giants, and Stephenson 2-18 remained, the quiet giant among giants, waiting. If this cluster already represents one of the most extreme stellar environments in the Milky Way, what happens when we finally measure the one star inside it that refuses to obey every known limit? There is a moment in every investigation when numbers stop being helpful. They stop explaining, they stop reassuring, they stop fitting inside the mental boxes we built to feel safe. For me, that moment came when the measurements stopped shrinking. They only grew, because the problem with Stephenson 2-18 wasn't that it was large, it was that no matter how carefully we measured it, it refused to become smaller. When measurement becomes confrontation at first, I trusted the process. That's what science teaches you to do. Trust the corrections. Trust the margins of error. Trust that uncertainty will soften extremes into something manageable. So when early estimates hinted that Stephenson 2-18 might be enormous, I expected later revisions to pull it back down. They always do. Distance gets refined. Dust gets recalculated. Temperatures get adjusted. Extreme stars usually shrink into reason. But this one didn't. It expanded. Every time astronomers improved a parameter, distance, extinction, infrared calibration, the radius didn't decrease. It climbed. That was the first time I felt genuine unease, because uncertainty usually protects us from monsters. This time, it was exposing one: distance. The first lock falls into place. The earliest size estimates for Stephenson 2-18 were handicapped by one major problem: distance. If a star is closer than we think, it appears brighter than it truly is. If it's farther away, we underestimate its power. Stephenson 2 sat deep in the Milky Way's inner spiral arms, roughly 19,000 light-years from Earth. That alone made distance measurements difficult. Dust distorted parallax, crowding confused signals. But as methods improved, especially with modern astrometric data, something unsettling happened. The distance didn't shrink, it stabilized. Stephenson 2-18 wasn't a foreground imposter. It wasn't cheating the numbers by being closer. It was exactly where the cluster was, and that meant its brightness was real. The excuse that ran out dust had always been the convenient explanation: too much extinction, overcorrected brightness, infrared contamination. But as dust models improved, astronomers began applying multiband extinction corrections, comparing how the star's light behaved across different infrared wavelengths, and every model agreed on one thing: the dust was heavy, but not heavy enough to explain the star away. In fact, once corrected properly, the star became even brighter. That's when the excuses started to disappear. Dust was no longer hiding the truth, it was revealing it. Temperature, the most dangerous number. Brightness alone doesn't tell you size. Temperature does. This is where things turned from unusual to impossible. Spectroscopic observations placed Stephenson 2-18 firmly in the late M-type range, around M6. That means a surface temperature of roughly 3,200 Kelvin. Cold, dangerously cold for a star this bright. And here's the rule that trapped us: a cool star cannot be extremely luminous unless it is enormous. There is no workaround, no hidden variable. No clever trick. If a star shines that brightly at that temperature, its surface area must be colossal, which means its radius must be absurd. The equation that cornered reality once temperature, luminosity, and distance were locked in. Astronomers did what they always do. They calculated the radius using the Stefan-Boltzmann relation, a simple equation. Cold, impersonal, unforgiving, and the result shattered the scale. The first serious estimates pushed the radius beyond 1,500 times the Sun. That alone would place it among the largest stars ever measured. But it didn't stop there. As data improved, the radius climbed again and again until the final accepted range emerged. Between 2,150 and 2,500 times the radius of the Sun. At that point, the numbers stopped sounding like science. They sounded like exaggeration, but they weren't. When the solar system becomes a measuring stick, I had to visualize it. Numbers that large mean nothing on paper. So, I placed the star where the Sun is now. Mercury disappeared instantly. Venus followed. Earth never stood a chance. Mars vanished without ceremony. Jupiter, deep inside. Saturn, still inside. The stars' outer layers stretched beyond Saturn's orbit. And this wasn't poetic license. This was geometry. Why this shouldn't exist. Stars are not supposed to do this. Every model of stellar evolution predicts limits. As stars expand, gravity weakens at the surface. Radiation pressure increases. Mass loss accelerates. At some point, the star should shed its envelope faster than it can expand. That point is supposed to be the end. Stephenson, 2218, crossed it and kept going. That's what makes it terrifying. Not just its size, but the fact that it sits beyond the expected boundary of stability. To comparisons that collapse, astronomers compared it to every known giant. Betelgeuse, Vicanus, Majoris, Uy Scuti, all famous, all enormous, all smaller. Even stars, once thought to be the largest known, fell short once their measurements were refined. Stephenson 2218 stood alone, not slightly larger, decisively larger, by hundreds of solar radii. The moment the language changed, this is where I noticed something subtle in the literature. The tone shifted. Words like candidate disappeared. Possible gave way to consistent. Caution turned into confidence. No, one declared it casually, but the conclusion became unavoidable. This was not just a red supergiant. This was a red hypergiant operating at the extreme edge of physics, possibly the largest star ever measured, with credible data. Why credibility matters? Astronomy is littered with exaggerated giants, stars that looked huge until distances were corrected, until dust was re-modeled, until better data shrank them back down. Stephenson, 218, survived all of that. Every independent method pointed to the same range. Different teams, different telescopes, different assumptions, same answer. That consistency is what makes it real and frightening. A star too big to ignore at this point. The story stopped being about discovery. It became about acceptance. Accepting that the Milky Way contained something we didn't expect. Accepting that our models were incomplete. Accepting that the galaxy had hidden its largest star behind dust. And we only noticed because technology finally cornered it. Stephenson 2218 didn't announce itself. It waited until we were capable of being disturbed by it. Standing at the edge of the scaly, imagine the moment astronomers realized what they were holding. Not excitement, not celebration, silence. Because when something breaks the scale, it doesn't just add a new record, it forces you to redraw the map. And we weren't done yet, because size is only the first layer of terror. Stability comes next. If this star is truly this larger, then physics comfortably allows. How long can something this unstable possibly hold itself together before it collapses?